Well, good afternoon, everyone. So this is a review for section 6.5. And 6.5 has a lot of motion problems, and I've already given you some of those, and I really like them, and they're really common, and they're really useful. So guess what? You're going to get some more, because it was a little bit quiet in class today when we were talking about some of the motion problems. So my sense is it wouldn't hurt to do a couple more. And if you're really, really confident with these motion problems, then you can just fast forward to the second part and check that. I'm going to work two problems today. So there's something inherently funny about a bowling ball and a cliff. You know, kind of a road runner, Wile E. Coyote bowling ball rolling this way. Bowling ball and cliff, I like these. So let's say our cliff is 375 feet high. If you're going to have a cliff, you might as well have a good cliff. And here's the ground for it to fall on. And let's give the ball an initial downward velocity once it goes off the cliff of 30 feet per second. So that thing's moving. And today in class we were talking about if you count this is 0, or if you count this is 0, at the top 0, at the bottom 0, it really doesn't matter as long as you're consistent. Let's say we want the height of the ball, h with respect to time, in meters above the ground. Meters? And I don't know if I like that, because didn't I say it was 375 feet? Let's change that to meters. Let's be consistent. This is a really high cliff. H of t in meters above the ground. Meters above the ground. And initial velocity. Function of time. I think we can make that one work. Okay. So we'll say that h of 0 at time 0 equals 375 meters. So we're starting at the top, and that height will get smaller as we get closer and closer to the ground. So then v sub 0 in this case will be negative 30 meters per second. And I wanted to start with a v sub 0 of something other than 0, because we've had a lot of those lately. I don't want you to assume that v sub 0 is always 0. Since we're in meters, acceleration with respect to time due to gravity will be negative 9.8 meters per second squared. Okay? And based on that, we can say that, okay, so as we talked about before today in class, we can say that the integral of a of t, the acceleration with respect to time, dt, equals the velocity with respect to time. In this case, that equals, well, maybe I better go down here. I think I'm going to run out of room. That is the integral of antiderivative, I guess, really, because I don't have limits of integration. So the antiderivative of a of t is negative 9.8 t to the 0 dt. And that equals negative 9.8 t to the first over 1. And I know I'm putting in the t to the 0, which you really don't see it, but that allows you to see the process here. Okay, equals v of t. But we're trying to find, how did we define it? I used h this time instead of s. So height with respect to t is what we're trying to find. So we're doing pretty well. So then we can say the integral of the velocity with respect to time equals the height with respect to time. And I guess there'd be, and again, I keep saying integral, but that's actually an antiderivative. V of t dt equals h of t. So that would be the antiderivative of negative 9.8 t to the first dt. That is the or I'm just going to evaluate that. Forget that. That equals negative 9.8 t squared over 2. And that equals negative 4.9 t squared. Okay, so now we are ready to jam on this. So we've got a couple of things to keep in mind. We have to do gravity. We have to do initial velocity, which was v of 0, and it was downward. Man, this thing's flying. And then we also have to consider the height that we started at. We'll just say, mess, h of 0. And that was up 375. Okay, so we can do this then. Let's put it all together. So the height with respect to time equals negative 4.9 t squared. Our initial velocity was a negative 30 t. Our initial height was plus 375 meters. Okay, I think that should be good. But maybe you don't believe me, okay? So jot this down real quick, or pause it, or whatever, and let's test it out. This will be kind of fun. Let's bring in our calculator. Okay, and first off, well, before we graph anything, I can see that this is in the wrong mode. This is in function mode, and we've got an equation with the parameter time. So let's, oh wait, no, I didn't do 2. We just did 1. This should work. Never mind. I was thinking in parametric mode, but since this is a quadratic, it should work just the way it is. It's kind of too bad because I like parametrics, but I'm babbling. Okay, so we should be fine. So we can go negative 4.9. We don't have t, so we're going to say x squared minus 30 t, x in this case, plus 375. And then we're going to have to set our window because it's going to be a lot. So 0 is good there. X max, that thing is going to go a ways. And, well, maybe not. It's just dropped. Let's start out with 50, and we may want to cut that down later. I'll make a mark every 5 meters. X min, negative 10's fine. X max, however, we really got to have to change. So let's go 400. And let's make a mark every 50. I think that'll be about appropriate. Okay, and then let's go back here, and let's do the ball trick. I always enjoy these. So you go way over to the left, hit enter a few times, like 6 times. I went one too many. I keep going past it. Okay, it's after the one more. I'm going to quit there. Okay, let's see how this works. Here we go. Cross your fingers. There's the ball. Boom! It hits. That is beautiful. Okay. Maybe if we want to see it a little bit better, you cut this down. As we suspected, it didn't travel very far in the X direction. So you could go and make this X, 10, and make a mark every 1 foot, and then we'll really be able to see it better. I love that. Love that. There's the ball flying off the cliff. Boom, hits the ground. So that works. Life's good. And negative 4.9 t squared minus 30t plus 375. I'm going to pause for a second, get up for the second one, but don't go anywhere. You won't even notice. Okay, I'm back. I took a little time to draw out the second one. And I was trying to do like Mo and animate these, but they started in. I want them to start out. And anyway. So here's the situation. Here is Colton, the astronaut. Hi, Colton. And he is on the moon doing research. And he wants to build a tower that looks something like this so that he can go up on the tower. Here's Colton, the astronaut. His plan is to go up on the tower and take moon rocks. Here's a moon rock. He wants to take moon rocks up on the tower and drop them off and at various heights and research what happens when they hit the moon dust. There's dusty moon down here. It's been there for a long time. Okay, and I love these falling ones. And I was thinking about putting another astronaut down here to get hit in the head with the moon rocks, but I'm not going to do it today. Okay, so he wants to figure out how tall to build the tower that will allow him to gather data for up to 20 seconds. He might want to drop it for 5 seconds, 10 seconds, 15 seconds, and then finally 20 seconds at the top. At least that much. Acceleration with respect to time on the moon is negative 5 feet per second squared because the moon is not as massive as the Earth. So these are the constraints we're working with. And you can be the engineer in Houston and design this tower for astronaut Colton. Okay, that's the setup. Now, we know that, as in the last problem, the integral of acceleration with respect to time, other way around. I am tired. It's 5 o'clock. I should go home. Acceleration with respect to time equals, yeah, that's it. Okay. Integral of acceleration with respect to time equals velocity with respect to time. And again, it should be antiderivative. I'm saying that a lot tonight. This time change is killing me. Antiderivative of acceleration with respect to time, dt, is the velocity with respect to time plus c. And so if we take the integral of negative 5 feet per second dt, we will get negative 5t plus c. Now, in this case, since astronaut Colton is just dropping them out of his hand, initial velocity will be 0. So we can say that velocity with respect to time in this case is negative 5t plus 0, or just negative 5t. And then, as we did in the last problem, the integral of velocity with respect to time equals the height of the tower with respect to time plus c, and antiderivative dt. Okay, so then, let's not use h. Let's go back. I want to mix it up so you're familiar with both. Let's go back to s, position with respect to time. You'll see both. So I want to use both. And I always want you to be bilingual. And so we can say that the position with respect to time equals the integral of negative 5t dt, the antiderivative again. I know I'm saying that a lot tonight. Antiderivative. So that would equal negative 5t squared divided by 2 plus c. And so in this case, c equals initial height, position at time 0, or the height of the tower. So we know that our time is going to be at least 20 seconds. So we can say S of 20 equals negative 5 times 20 squared divided by 2 plus S sub 0. And in the end here, we're trying to find the height of the tower, S sub 0. And so that's the height that Colton will be dropping the moon rock. But that's the maximum height, so that'll also be the height of the tower. So now we can say S sub 20 is when it hits the moon, the surface of the moon, and so that height is 0. And then this is negative 5 times 400 divided by 2 plus S sub 0. That is 1,000 negativo plus S sub 0. You can see where it's coming from. 1,000 equals S sub 0. And those units are, we were in feet on this one, I think. I might have said meters. Feet per second for gravity, so this will be in feet. We always want to make sure our units are right. 1,000 feet equals S sub 0. So the moral of the story is, tell Colton, I should respect astronaut Colton with a capital. Tell Colton the astronaut that you will design a moon tower that is 1,000 feet tall. You're saying that's an awfully big moon tower, but think about it. On the moon, gravity's not that big of a deal, and there's no wind, and I don't know if there are earthquakes. We'll have to discuss that in class. But I would think you could design that tower with some pretty flimsy material, and it would stand just fine. Food for thought. All right, everyone. Have a great evening, and I hope this is helpful for tomorrow's quiz. Good night.